All right, good afternoon. How you guys doing? All right. I am almost completely better. I have a tiny bit of congestion still, so hopefully I'll be fine. I did pretty well till the very end of my last class, but now I have another class, so we'll see. But hopefully, if at the worst case, I think I would just need some water, or go clear my throat or something. Okay, so looking at where we're at with the syllabus schedule, I've made an update. I haven't posted it to Moodle yet, but I will. My current plan is to continue with gas transfer for the moment, for today. That'll take another lecture or two, and then we'll get into adsorption. I probably need to update this as well, because I think we probably need today and the 21st for gas transfer. And then we'll begin discussing adsorption, and then this week I will be out of town. So during this week, I'm going to use that moment to give you a guest lecture. I have a PhD student who will graduate soon. Has been working on advanced oxidation processes, which we will cover kind of in the next segment. So you'll get a bit of a preview and a research flavored talk about that. So that'll be on the 30th. And then for the 28th, instead of class, I'm going to essentially assign, and you can do this at any point, a makeup lecture and a lecture, both asynchronous, for kind of that topic. I do have materials and things recorded, so I can provide that, the links and everything for you. That'll allow us to make up lost time and cover the adsorption stuff, and then when I return, we can discuss anything outstanding about the adsorption at that point. So that's my plan for the moment. If you have any concerns, I'm definitely open to it, open to hearing it, but that is currently the plan. And then hopefully we'll be back on track. I'll have an exam. I'll get your next homework posted. I'm going to aim to have that posted for you before fall break, so you'll have that to work on at your leisure. All right. So with that, I had one other thing I wanted to mention. I took a bit of a delayed look at kind of the overall picture of how the exam grades came out, and someone also brought to my attention that I had it marked as out of 110 points possible. Did not mean to do that, and I was scoring it as if it was out of 100. In theory, that would be in your favor. In practice, that actually might signal to me that I ought to be taking more points off per problem because there was a larger number there as a function. So I don't know exactly if that mattered much, but I did notice that the highest mark was an 89, and so I'm considering bumping everybody up 4 points to make that at least scratching the lower part of an A. So A minus, or as the highest mark. So I will probably do that. I'm still finalizing my thoughts on that, but just want to let you know. So if for whatever mistakes I made, I think that would account for it. All right. Okay, so with that, I want to talk about gas transfer. We left off last time we were talking about it, and we were really diving into, okay, what are the Henry's law? What's the Raoult's law? How do these work? Why do they work? That kind of thing. And then we got to a practice problem, and we got most of the way through it. So we had this problem where we have the Henry's law, constant for oxygen, and then we were tasked with A, expressing that constant in the form of an atmosphere per mole per mass. B, the Henry's constant as HPC. We'd have to kind of go back to take a look at what that refers to. There's different formulations. So PC would be the partial pressure, And finally, C as dimensionless. And we kind of left off there saying that, okay, that we're probably going to need the ideal gas law for that one. And the reason is because the dimensionless one, we need a concentration per concentration. So the Henry's law constant, again, is giving us the ratio of the amount of a gas in a dissolved versus gas phase, right, in some system. So if we want it dimensionless, we have to have the same units in gas and in the liquid phase. And one convenient way to do that would be to say, take moles per liter of this of oxygen per liter of water divided by scenario to get HCC as a dimensionless one. We need to calculate the concentration of our oxygen in air. So we have, was it already given? Excuse me. So we're looking at oxygen here. So we're given this 769. This is atmospheres per liter of the liquid. So at 1 atmosphere, we have that many moles per liter. We don't have 1 atmosphere of oxygen, however, and so that's where we need to go with it. So take a moment and using PV equals nRT, it's our ideal gas law, with R being 0.082 atmospheres liters per mole Kelvin. We're at 25 Celsius, so the temperature should be 298.15 Kelvin. Let's see if you can arrive at the answer here. some progress. So essentially what we have is some amount of atmospheres of oxygen per mole per liter of oxygen in the water is one way to look at this number, right? Almost 800 atmospheres of oxygen will be in the atmosphere if there's 1 mole per liter of oxygen in the water at equilibrium. So that's our HPM is what it was calling. And we want this HCC, which is meaning we need to put it in moles per liter divided by moles per liter. So if we take a look at the PV equals nRT formulation, we could consider an arbitrary 1 liter or something and say, okay, how many moles in that 1 liter? That would be an approach. Or we could simply solve it for N over V, say what is the number of moles per volume in this situation, as long as R is in liters. So you can have an R in cubic meters or something. But we have this R in atmospheres liters per mole Kelvin. If we rearrange, N over V is equal to P over RT. So if we need to convert from the pressure as a concentration unit into moles per liter, then this would be the way to do it, right? So we can take, we can say this dimensionless constant would be effectively the pressure-based constant. We'll say PM, I think, right? Divided by RT. So we would get 769 atmospheres per mole per liter divided by R, which is 0.082 atmospheres liters per mole Kelvin times 298.15 Kelvin. And then let's just check to see what happens to our units. Our kelvins, of course, will cancel. Our moles on the bottom here will go up to the very top. Atmospheres will cancel. And the liter here will travel also to the top as moles per liter. So all of that should work out nicely, and we should get 31.5 moles per liter per moles per liter, essentially. You could also maybe just leave it as the moles will directly cancel, and we could say that would be liters of gas per liters of liquid, I guess, right? Oh, sorry, I have that backwards again. Liquid over gas. Okay. Yeah, because it's in denominator. All right, makes sense? Okay, so I want to do the next problem in line, but I'm going to go ahead and bring up the next set of slides for that because I have that there as well. All right, continuing to build from this table 5.2 to make a little bit of use of it. We're going to take a look next at cyclohexane. We see it's slightly, slightly happier to be in water than oxygen, but not by a whole lot. So we got a Henry's law constant of 182 in that pressure per concentration form. And we have an example here that says we have received a sealed vial containing a water to be analyzed for cyclohexane. The volume of the vial is 10 milliliters, so it's a little vial. It's at 25 Celsius, and you notice that the vial has a small air bubble with about 0.25 milliliters worth of air. Okay, so assuming cyclohexane is volatile, which it is, we kind of expect some of that cyclohexane to partition into the gas phase. So the question is, if the sample originally contained 10 to the minus 7 moles per liter of the analyte, cyclohexane, what concentration will you measure in the solution, assuming it has equilibrated with the bubble? Then part B, so that's part A, and part B says what are the concentrations of cyclohexane in the gas and liquid phases of the bottle in micrograms per liter. And they give us the molecular weight is 84 grams per mole. Okay, so take a few minutes and consider what the situation is and see if you can solve that. How you feeling? I'm getting there, but not quite there yet. Stuck? Bored? Sleepy? All right. So you can probably see how I've set up the problem a bit, and kind of gave a bit of a starting point here. We have a 10 milliliter bottle. Now we are told that it has a solution in it, but we are told that the vial itself is 10 milliliters. So I think the best assumption is to make that that's 10 milliliters that the vial can hold, and then we're also told there's an air bubble in it that has some volume. So that volume should take away from the solution volume available. So that's 10 milliliters total, some portion of it's air, therefore we don't have a full 10 milliliters. And so that's where I went ahead and wrote down, okay, V air, 0.25 milliliters, V total, 10 mils, and a V liquid at 9.75 milliliters. We're given a total concentration, so the sample originally contained 10 to the minus 7 moles per liter of the analyte. And I think the assumption here is that we took a liquid sample, it had some concentration in that moment, shoved it in a vial, and it was kind of supposedly gas tight, right? And shipped to us for analysis or something. So if we know that it was originally 10 to the minus 7 moles per liter, what concentration will we measure in solution now that it has equilibrated with that air bubble? That's the task. So we have to recognize that we have some total number of moles that's going to be 10 to the minus 7 moles per liter times the volume that the liquid occupies. So it's moles per liter times liters. We put that 9.75 milliliters into liters. That should give us 9.75 times 10 to the minus 10 moles in that bottle. So then we need to recognize, well, some of that's going to the air phase. That's where we say, well, the total number of moles total is going to be split between the air and the gas. And that we could define the moles here pretty simply. The concentrations are obvious for the liquid, right? So the concentration of the liquid times the volume of the liquid. We were kind of just working from that type of perspective. And then the gas, we simply need to find the concentration of the gas and in that tiny little volume of gas. So there's where we need our Henry's law constants to say, okay, well, if we have some total amount, where is it partitioning into? So we can define concentration in the gas phase according to pressure. So using the PV equals nRT, the ideal gas law, right? We could say that the concentration, just like we were doing a minute ago, N over V should be, what was that? P over RT? P over RT, which is what we see right here. Okay, so then multiply that by the volume, kind of, volumes are going to cancel, and we should be able to get a value for the pressure in that system. And then likewise, we can take and then find, given that value, that pressure value, convert it using our HPM, the Henry's law constant that's going to convert from the atmospheres into our concentration of the gas phase. So if we say HPM is equal to pressure of the gas divided by concentration of the liquid, we can put concentration of the liquid right here, or rather put the other side of that equation, rearrange that equation for CL and put the P over HPM there. Now, we actually don't know the pressure yet, so I think what we're building here is kind of a system of equations or two of the same unknown to solve. All right, so if we put that together, we can say, all right, this P, the pressure of the cyclohexane, I'm just putting I, this should be equal to the N total divided by Vg over RT plus the VL divided by HPM. Essentially what we're doing is we're taking the fact that N total is on the other side of this equation, and we are factoring out the pressure and rearranging. Okay. And with that, we can solve and find that the pressure should be 1.53 times 10 to the minus fifth atmospheres. And from there, we can calculate each piece that we needed, right? So now we can say our CL, concentration in the liquid, which is really kind of what we're after. That is this pressure divided by H, Henry's law constant in pressure per moles per liter, HPM. And so that will essentially be the 1.53 times 10 to the minus fifth atmospheres divided by 182 atmospheres per mole liter, and that'll end up giving us a value here. So I'll go ahead and write that out. And this 182 value is coming from our table 5.3. Okay. When we do that, that should come out to be 8.4 times 10 to the minus 8th moles per liter. So what we can see is if the solution initially contained 10 to the minus 7 moles per liter, then we have this small little air bubble. Suddenly it's measuring at, I guess, 0.84 of what it used to be. So 15% approximately of the amount, the molar amount of our cyclohexane is in that tiny little bubble. All right. Okay, so does that answer the question? What would the measure be? Yeah. Okay, so that's part A. Get some more space for part B here. So at this point, it's a little bit straightforward. Now we just simply need to convert from moles per liter into micrograms per liter. That's not so hard. I guess maybe we need to find the concentration as moles per liter in the gas phase, but we already kind of did that same thing in the previous problem as well. So just to briefly show you what the solutions look like. We can take that 8.4 times 10 to the minus 8th moles per liter and multiply it by this 84 grams per mole, or 84 times 10 to the 6, not 16, micrograms per mole. And we'll get a value of 7.0 micrograms per liter. Concentration of the gas. Here we need to make use of that Henry's law constant. Would be handy to go ahead and use the dimensionless one, the moles per moles per liter one. This was given. Again, we could look that up at the table, but put it here at 7.44. And when we're calculating for the concentration of the gas, the nice thing is we can just simply take that and multiply it by our concentration in the liquid phase. So since we've already done the moles per liter conversion, and I mean, we could go and undo it and then redo it. It doesn't really matter here because we can basically just, like, it's a factor, right? We're multiplying it by a factor. So we can actually just go ahead and plug in the 7.0 micrograms per liter. It's the same species molecularly, so no problems there. We can just simply say concentration of the gas will be this 7.44, and we can track the units. This would be liters of liquid per liters of gas times the 7.0 micrograms of our stuff per liters of liquid. And so ultimately that gets us, we'll convert that liters of liquid into liters of gas is the idea. Right, so then we get concentration in the gas phase is 52 micrograms per liter of gas. Yeah. We didn't consider the cyclohexane in the gas phase, and we considered just the one in the liquid phase. In part A at the very beginning, the assumption here is that it says originally contained. So the originally is telling me that, so first of all, it says originally contained, and then it says, then it's asking what concentration will we find, assuming that it has equilibrated with the air bubble. So the problem is implying that there wasn't supposed to be an air bubble. And originally, before there was an air bubble introduced or there, it had this concentration. So originally all of the solute was in the water phase. And then accidentally we introduced an air bubble is kind of what the problem is trying to say. So the air bubble is from the atmosphere in or from the liquid? Correct. It was as if I was trying to fill my water bottle, and then you realize that, like, there's a little space up here and at the top of this space that just lets a little extra air be there, and you just didn't quite get it all the way sealed or all the way airtight. That's my interpretation, and that's how the book was approaching it. Okay. All right, good. Yep.
Like using dimensionless, you can substitute H prime for concentration of gas over concentration of liquid.
Yeah.
And then substitute that into your mass balance for the CV plus CV.
Okay. I see some other people nodding. Is that what you were doing? Some people? Not everybody, but some. What's that?
It gives the same result.
Yeah. Yeah, there's very likely a few ways you can go about it. I mean, if you wanted to, you could probably convert it into some other strange unit and then back, but I think the principle here is that so you did a substitution, right? And in the book solution here, essentially it's, instead of substituting directly, it's factoring out something. But in some sense, it is substituting a pressure value instead of the concentration in the liquid value. So in that sense, it is kind of a substitution. And so it's a system of equations. At first, there's two unknowns. We make some substitution, and now we have one unknown. Yeah, and I actually think that I solved it differently last year. And I didn't have those. I mean, I had them, and then I erased them, and then I decided I would just go with how the book did it this time. Okay. All right. So back to kind of how gas transfer is working. Ultimately, where I want to head next is to understand the principles of what drives the air transfer so that we can have a better appreciation for the models that predict, okay, how well is aeration working? Or what kind of flux of gas do we get across some boundary? Does it matter? Are we mixing the fluid? How wide does it matter? Things like that. So we want to talk a little bit more about the dissolution process, the gas dissolving process, or degassing. And that brings us back to, okay, what is really happening when a gas enters the water? Well, solvent interactions are one of the key components. So water being a solvent, you could also consider some other solvent and a gas dissolving into it. What's going to matter really is the interaction between the gas molecules and the solvent molecules. So, for example, we have this little hypothetical molecule and a bunch of water molecules at each of these vertices that are there kind of creating some sort of a cage or a solvation shell around it. And maybe a better way, instead of just writing a H2O here, maybe I could show essentially it would kind of look something like this, where we have a water and a hydrogen, and then the neighboring water is kind of bonding with that guy, has its own hydrogen, and so on. And they're sort of branched, connected in a loose sort of manner, right? Each water molecule we can think of as kind of hanging out with its neighbor, sort of. And the hydrogens will probably want to interact with the oxygens. And in this particular case, this diagram is showing what would happen if you have a hydrogen-bonded water molecule surrounding a hydrophobic solute, meaning that ball in the middle is not very polar, and water doesn't really want to interact with it directly. It would rather interact with its neighboring water molecules and just form a little cage and surround it. Now, it turns out that that interaction can become a rather tight interaction, because if you imagine each of these water molecules pulling on each other on that cage, you could get water very closely packed to that hydrophobic thing, even though we normally think of hydrophobic as a weak or kind of repelling type of interaction. In this particular case, it kind of is a little counterintuitive, and we could have some tight interaction. All that to say, this is the type of interaction that's going to dictate whether or not a gas molecule wants to stay in the water, or whether or not it's going to pop back out. So things like the octanol water partitioning coefficient we could consider. That is as a very similar topic to our Henry's law constants. Tells us a little something different. It's more about how much a given molecule wants to stay in water versus octanol. You can do it with other solvents too. But usually that tells us something about how likely a molecule is to hang out in water compared to something that's less polar. So the octanol water partitioning coefficient might also tell us something about the volatility. If it doesn't like hanging out in water, maybe it's more prone to popping out and leaving. Okay, so maybe if these interactions are not very thermodynamically favorable or not very sticky to that molecule, maybe it's going to head off. So if we go back to the very beginning of when we're looking at, not I guess very beginning of today, we're looking at these different molecules about what likes to be in water versus what does not like to be in water, we might see a little bit of that. We might see that some of the things that prefer hanging out in water perhaps have more charge or more polarization than things up higher on the list. So something that we might consider there. There are other factors, orientation that the structure makes, like I said, but also things like other molecules around that might disrupt or enhance or change what's going on there. Entropy, meaning temperature, largely, right? So if we have a high entropy system, it's a lot easier for some gas molecule that had been surrounded by water and kind of captured, so to speak, by the solvent to escape, right? So if that molecule is at the surface and it is not being kept by some interactions, it's likely to float away, volatilize. Okay, so a little example here. The presence of other ions can be important, chloride in particular. This is actually one reason why we tend to monitor it in natural systems. If we have a stream and suddenly there's some contamination that brings in a lot of chloride, it doesn't sound like a big deal, but it can actually affect the solubility of oxygen. So even if it's largely harmless, if you do have a big chloride input, not to the level where you're making it like salt water or whatever, but if you do have an input, you can be disrupting the system based on how much oxygen is dissolved. So here's an example going from basically fresh water all the way up to seawater. And Lake Pontchartrain tends to be somewhere right around it here, in case you were curious. So if you have chloride dissolving, you'll see this is the oxygen concentration in milligrams per liter at a given temperature. So we could say, let's say it's 20 Celsius. We could find how much oxygen we expect to dissolve. If we are in seawater, that's something like 7-ish milligrams per liter, whereas fresh water might be more like 9 or so. Okay, so it's not a massive difference, but it certainly is a difference. It does depend on the particular solute. This one's chloride. Some of the others are a little funny. Sometimes they're not predictable in this way. Again, molecular interactions do get complicated, so certain molecules might enhance or otherwise change the dynamic. A lot of it, though, has to do with disrupting or altering the hydrogen bonding within the water solvation shells, like that solvation dynamic. Okay, I mentioned temperature already, but how might we deal with it? Well, we have the Van't Hoff equation. This essentially would, what we can see if we plot the Henry's law constants as a function of temperature, essentially increasing temperature always decreases the solubility. So always increases the H. So with increasing H, that means more of it's going to be in the gas phase, more of the gas in question. Here's a log plot for that, and we can see on a log plot, it's a slight linear increase for most of, for basically all of these gases. And again, that has to do with having enough energy to allow the solvation trap or cage to release something. So if everything's jostling around, it's more likely that something pops out and volatilizes. Kind of intuitive. You probably recognize that, hot water or hot liquids tend to evaporate quicker. It's all kind of the same thing. We have the Van't Hoff equation. If we need to use it, we can say, this actually works for many constants, but including the Henry's law, the natural log of the Henry's law at a new temperature divided by an initial temperature would be equal to the delta H over R times 1 over the first temperature minus 1 over the second temperature. So it's thermodynamics, seen that before, could use it if we need it. All right. So what happens if we dissolve something that can then have a equilibrium reaction and attain a charge? This is where I think kind of the gas phase chemistry becomes pretty interesting in the context of the world of aqueous chemistry, because essentially we need charge balance in any system, that's the principle of charge neutrality certainly holds in water, but it's also true that gases or gas phase things don't have any charge. You never have charge, a charged species. You don't have ions in the atmosphere. Unless you are ionizing things and then you have a plasma with ionic gas phase-ish type stuff. It's a little different animal there, but in general, we consider that gas phase, there are no ions. No charged particles unless something fancy is happening. Okay, so then in water, we have to have a net neutral charge, right? So that's the principle of charge neutrality in water or in solution. The net charge equals 0, right? And that has to hold true. So then what happens if we dissolve ammonia gas? Well, first, we have our equilibrium, the ammonia gas with, we'll say gas, with aqueous ammonia. But then, once we have aqueous ammonia in there, we have an equilibrium reaction between that ammonia and ammonium. In fact, I'm going to write it this way. So ammonium ion can release, what am I doing? Backwards. Sorry. That's what I meant. Ammonia could accept a proton, H+, and form ammonium ions. And so now suddenly we have a scenario where we have a gas, where we were going to do our gas, Henry's law balance. Suddenly, a portion of that dissolved gas is no longer able to volatilize. So a portion of our gas is essentially removed from the equation of equilibrium. Now that is because of a second equilibrium equation, so it does get a little squirrely here. But essentially, this guy cannot volatilize. This becomes pretty convenient if you are trying to do something, let's say like ammonia stripping, where you're trying to get rid of ammonia from the atmosphere. You might run a system where you're passing a lot of air across a lot of water with high surface area and all that, and you do it in a very, if you do it in an acidic environment, you are going to be adding a lot of the acids, right? Ammonia is a very basic species. It likes to take away the protons. So if we do this in an acidic environment, everything here that gets added to solution then takes a proton and becomes ammonia. And suddenly you are essentially driving the first equilibrium harder because this species keeps going down. It keeps dropping to a very low concentration despite the water accumulating the total ammonia, right? So that works for this scenario. This dynamic is also at play with carbonate. So in the case of carbonate, we first have CO2 in the gas phase in equilibrium with aqueous CO2. Then we have a reaction of aqueous CO2 with water. Gets us to carbonic acid. A lot of times you'll just see people kind of skip over that step a little bit and just call this HCO3 star. But we're going to leave that as is for now. And then carbonic acid is in equilibrium, and this is simply in the aqueous phase at this point, with bicarbonate, HCO3 minus, and a proton. Bicarbonate then will be in equilibrium with carbonate. And both bicarbonate and carbonate are charged and therefore cannot volatilize. So in the case of CO2, we can essentially fit more CO2, pull more CO2 out of the air if we simply make our solution more and more basic. Because each time we add some carbonic acid, if it's a very basic solution, those protons will be stripped away and we will end up with charged carbonate or bicarbonate species. Now, CO2 doesn't dissolve a huge amount, so this is not really a way to store a lot of carbon, but you can recognize that the pH of the water would really affect how much CO2 is dissolving in your total CO2, total dissolved CO2. All right, make sense? All right, so now I want to talk a little bit of theory here. And I kind of am just going to connect a few pieces that we've talked about a little bit. I think there are really high depth studies about this kind of stuff, and we're not going to quite go there, so I'm going to give you the bigger picture. We can imagine, and people do build models for understanding the transport of gas across the gas-liquid interface. And a couple of the common ones use what's called a kind of a particle or a packet type of approach. So if you can imagine a packet of water or liquid, and like as if you took a droplet and then put a little boundary around it, and then tracked that little packet as it's going around its business, maybe mixed, maybe not mixed, as it's hanging out, what is the gas inside that packet doing, and what is that packet itself doing? So that's sort of the question. So then we come to some interface here where we have, let's say, the liquid and the gas. And in kind of a short range area, there's the transfers that we talked about previously, right? The gas exchange is kind of going across here in some manner. We talked, depending on which one has more concentration, we could draw concentration profiles and everything. That's not really what I'm interested in, so I'll just draw this, like that. So we're having gas exchange there, but it can only happen for this little parcel, this little packet, if it's near the surface, near that interface, right? So if you, again, imagine if my little parcel is down at the bottom of my water bottle, there's no gas transfer happening. So considering that my bottle is filled with little packets of water, some of them are near the surface and some of them are not. So whether or not it's mixed will have something to say about how quickly this gas exchange will occur. So as this little packet moves to the surface, or maybe now it's there and now it moves away from the surface, those kind of dynamics turn out to be important. So there's a few different models that have been developed to try to estimate or to take some consideration of how long is that parcel at the interface or near the interface. Maybe we do a stagnant thing where it's there, we have many residence times of time where that parcel is there. Or maybe we do something where it's meeting the surface and going away, or different things like that. So there's a few mass balance models. Essentially, they're all going to make use of what's happening at the surface. So again, our typical mass balance for one of these gas transfer systems really what's happening at the surface, at that interface, is what we are very interested in. So we could go into that. The book kind of touches on it a little bit, but we're almost out of time, and I wanted to talk about kind of this sort of stuff. So if we have a bulk gas here on the left, and then a bulk liquid over here on the right, the scheme here is that in the gas phase, okay, diffusion happens a lot quicker, right? This is probably, for most of it, maybe up until a very small interfacial layer, that's all just what it is. In the liquid phase, that interfacial layer becomes very important. And it's a longer distance in terms of how far this interface is important. So if we take a look and consider that's probably our limitation to whether or not the gas is in the liquid or in the gas phase, that's where we want to take a look. So we could consider a flux across this interfacial area as like what's important here, and we could draw some arbitrary distance within that layer to do a mass balance on that. So then if we consider what happens if we bring that little packet, if we bring a little packet of water to the surface so that it can do this, can send a gas across one way or the other, can maybe accept a gas, maybe give off a gas. How long does that packet stay there, and what relevance does that have? So the graph over here on the right is discussing that. So the dissolved concentration, if we have some initial concentration that is high and it's going to give off some gas to the gas phase, and track that as a function of distance, at the bulk solution, we have, I think I said that backwards actually. So at the bulk solution, let's take a look here, our concentration is low. Cl, I'm just going to give this some numbers just so we can play with numbers. So Cl equals 1 in the bulk. Okay? And then over here at the interface, when we are right at the interface, the little example I'm saying is Cl is now 5, if that's a 5. So it's higher over here, lower here. The gas is pushing a lot of stuff in, but it's getting spread throughout the water. So if that parcel stays a long time there, then the transition is a slower one, meaning that the concentration as a function of distance from the surface just kind of drops like that. Whereas if our water packets are mixing rapidly, the concentration drops quite dramatically as a function of distance. So because we are replacing the water very quickly, new water shows up and is ready to take the gas. Okay, so that's kind of the idea here. So with increasing time, this is tau for the packet. So when you see the stuff like a surface renewal model or things like that, again, I'm not really getting into the heavy details. I just wanted to explain the concept here. That impact of the water approaching the surface and then leaving, taking away the new concentration to mix with the bulk is important. So even if the bulk is the same concentration in any of these cases, we get to that concentration, we get to that bulk situation faster in terms of distance away from the surface if there is less times for the water to spend at the surface. Fancy way of saying mixing will cause the gas transfer to happen quicker, okay? And to make all that occur. Now that can be very important if we're not yet at equilibrium, right? So in this case, we are finding some equilibrium, but if we are essentially operating on purpose in a state that's not at equilibrium, we could really drive gas transfer faster by exposing the interfacial layer to water that is further from equilibrium more frequently. Okay, so it has some big impacts on what's going on. Okay, just a little bit more here. We can kind of look at this as a diffusion process at that interface. Advection of that packet to the interface is important, but inside that interface, we really are talking about such a small distance that diffusion is what's driving the gas across, diffusion of these molecules. And so we could look at the distance from the interface, and again, the concentration, and the times here, diffusion times there. Okay. So for the overall mass balance, we can drive it just by the taking advection to 0 and no reaction, because we're doing it at such a small volume. Okay, I think that's probably all I feel like we need to cover. There's some more stuff that you could get into, but we're going to leave it there. Okay, so enjoy your fall break. We'll see you a week from today. Do a little bit more gas phase stuff and then get into adsorption.